We'll get started. All right. Hopefully everyone had enough to eat. So we're going to get started with the afternoon session. So we have three presenters this afternoon, and the first presenters are the Nobel Systems superstars. And that's what I call them, because they do some really amazing things, and most of you have worked with them in some capacity. And so these are the folks that are responsible for taking your feedback, making the modifications, and making the system work for you and your end users. So what they're going to do is they're going to show you some of our new stuff and let them, display it, ask questions. That's what they're here for. So please ask questions. So with that being said, we're going to turn it over to Aretha, Jabina, and Tamai. Excuse me.
Yes, so we're going to show some new modules, especially hydraulic modeling, IoT, and some other modules too.
Hello everyone, hope you guys had good lunch. So we'll start with the first module, which is Internet of Things. And so I think everybody heard Internet of Things in this event. So basically with Internet of Things, we're trying to monitor plane pressure. So this is where you can monitor pressure at the main lines, the lateral lines, or the air release valves. And this will help you improve pressure monitoring in real time, and also get some alerts if there is any high pressure, low pressure, or leaks in the system. So we have installed these devices. So these are plain cellular or LoRaWAN based devices. It's based on your requirement. If you have good cellular connectivity, we can install our cellular devices there. We use cellular devices from Digi. We have our some partners here too from Digi. Then we have these devices. So currently this picture you're seeing is from a LoRaWAN device. This is a plain pressure monitoring device where you can see the trends. You can see any spikes in pressure. You can see any transients in the pressure. This can be installed in less than 15 minutes, very easy installations. So just want to show you how this integrates to GeoViewer. So you get a button on GeoViewer saying IoT dashboard. You can see all the devices in this dashboard. You can click on that. You can see all the daily trends there. You can see the maximum pressure, minimum pressure, the battery level, and also the alerts in the system. So the reason why we wanted to put IoT is basically why are we using IoT from Nobel Systems? So where Nobel Systems comes in is we can pull all this data from these IoT devices, from your SCADA system, and push it into a hydraulic model. So we're building a real-time hydraulic model. I think Tom Coleman from Roland mentioned this in his presentation. So all this data is now pulled into a real-time hydraulic model. So this is how the model looks. So we have all the pressure layers there, we have the flow layers there, and this all data is real-time. So the benefit of using this live hydraulic model is, let's say you have a SCADA system in place. There is no current integration to the SCADA system where you can pull in all the monitoring data. Like we do not check on any of the control tags, but we check on the monitoring tags. And we have a backend which pulls all this SCADA system into this hydraulic model. We also have developed a program where we integrate all the AMI data from the meters and push it into the hydraulic model. And basically, the hydraulic model is now aware about the rules for the pumps and the tanks and what's going on in this system. So let's say you are using this model now. Let's say you have a model which was created. Uh, yes. So let's say you have a model that was created about uh, yeah, let's say you have a model which was created about 5 years ago, right? So now you can give us that complete base model files to us. We will push it into this engine from KTM. And you can give us read access to the SCADA system. We have a software, a very secured software, where it reads each tag from the SCADA system and pulls that data into this model. Even for the AMI data, we map all the lateral lines, the service connections to the model, and you can see what's the daily demand in the system. So I'll just play this video. Yeah. So this is just a snapshot of how the user is seeing the data right now. So you can see all the pressure layers. You can see nodes with very high pressure in the system. You can always turn on, turn off any layers for the pressure. So currently this turned off all the layers in the system. Now this is turning on the flow in the system. You're seeing the real-time flow, which complements very closely with the SCADA system. So if you see these lines with the flowing direction, this is the flow direction and the flow in your system. This is the tank volumes in the system. And right now they clicked on a pipeline. They can see the real-time data in that pipeline. This is yesterday's data in the pipeline. They can also, so this is a system overview. Now the benefit of this one is you can do any sort of fire flow analysis. So now this user is, so this is now closing a pipeline, and you can see the pipeline is closed, which nodes are getting affected, and what is the effect in the overall system. Like what's the pressure at the nodes, what happens at the nodes, what happens at the pipes in the system. So basically a normal field guy or a field person is also getting a view into the hydraulic model. I do not know if currently any field guys have an access to the hydraulic model, but using GeoViewer and this system integration, they can see all the pressure transients in the system, the pressure overview in the system if a pipeline is closed. So right now the user is clicking on a hydrant. So he just selected the hydrant and he wants to, yeah, so I just closed a scenario and I'm creating a new scenario. So right now the user just clicked on a hydrant and they want to do a fire flow analysis. So I'm just increasing the demand. So in fire flow analysis, you guys often increase the demand and see if it's meeting the minimum 20 PSI requirement or what is the changes in the system if the flow is increased. So right now it's simulating, and at this node, it found out that at 917 gallons per minute, the pressure will be 47.1 PSI. So that's how you can create different scenarios. You can also open a pipeline, close a pipeline, increase the pressure across a hydrant and see what the system will look like. So that was the hydraulic model. So one of the useful thing in this model is like for Roland Water District, it's a very good case study. We created this model and they often update their GIS information into our system. And this GIS information is updated into the model in real time. Like if you guys add a new main line or new pump station into the system, we add this into the hydraulic model. Now what happens is like you do not have to contact the engineering firm every time to update your hydraulic model. You can just tell us that you have updated this in the GIS, we'll update it into this model. Now let's say if you have a little bit idea about the hydraulic model, there are certain rules in the model where when the pump is normally open, when the pump is normally closed. So not every person in the system knows when a pump is normally closed or normally open. So what we do is, because we're getting the real-time SCADA data into the system, this information is fed in real time. Every 15 minutes data is fed into the system. Now, instead of the field guys knowing it first, I mean, all the field guys knowing it first or all the operation guys knowing it first, the model knows that this pump is normally open or this pump is normally closed. And that's how it keeps on updating. All the flow information, all the pressure information is updated in the system. So instead of using the hydraulic model every 5 years, or I mean once in every 5 years, you're using the hydraulic model every day for your day-to-day operations. So that's the benefit of going with IoT hydraulic model. The next step for this is, Tom from Roland was showing you using this data into the CIP program. So let's say you close a pipe. I mean, that's our next step. We are going to integrate with Fracta is that we are going to close up, let's say you close a pipeline, all that information of what happens when a pipeline is closed, right? That information will go into this AI model, or what are the consequences of this pipeline failing. And based on that, we'll grade that pipeline. So this is the next step for this model. But yeah, I mean, you can always use this model in real time, every day, and manage your operations. So yeah, I think for the next part, Arita will help you guys with this. Do you guys have any questions with the IoT or the hydraulic model?
Just on the security part, like we have this theory that SCADA should be kept separate of GeoViewer right now, and I don't know why. And how do you change the people that are in charge? You know.
Right. That's a very, very common concern we have always. So basically, first we don't even touch the actual SCADA system. It's like we have a software where it integrates to the historian. And we talk to you guys and check which are the tags which have only read access and which are not controllable. So all these basic pressure parameters, right, like the pressure, flow, all these parameters are only monitoring purpose tags. So we just integrate with those tags and get the data in. In that integration software, there is a module which specifically restricts any user using that software to have no access to the control tags. So we just read the data every midnight and push it into the model. So yeah. Okay, I think Arita, you can.
Next, we have a customer engagement module. So this is for cities, so the citizens can download the app and submit issues to the city itself. So we've developed an app for the citizen to report potholes, graffiti. We can submit photos, and it automatically creates a work order in GeoViewer. I'll just play the video. Oh, so we can create a ticket here. This is an app on your phone. You can choose an issue. You can also type your comments here. And you can enter the name. These fields are all customizable for the city's needs. And here we can add photos and videos. And then all of this information will be saved and sent directly to the staff. Play video. Yeah. And so here you can see all of the complaints come into the customer complaints tab. We could see the information here, who created it, and so this comes into the internal staff's app. So they get immediate notification, and then they can close the ticket, update information, and it will be, once it's closed, it will be sent back to the citizen. Here you can add labor and material information, and this will subtract directly from the inventory. And so here I'm uploading the material, and then I could take an after picture too, and that now it will be saved. So we built these apps so it allows no need for coming back to the office or phone calls. Directly the citizen will create the complaint, it goes into the field guy's phone, he'll complete it, and it's done. So there's better transparency with the citizens. We also have a tool now, there's a new EPA guidance rule, requirements for lead and copper rule revisions. I know you guys have a deadline to implement a solution for building this inventory before October 16, 2024. We are developing this module with OMWD, Roland, VCWD, and so eventually we will be servicing it out to all our customers. This is a module that inventories all of the lead and copper lines in your system. So here, once you select LCRR from our app, it will highlight all of the meters here on the map. And so we'll give you 1 year to go through the whole system. You'll click on the meter itself, and then here you will fill out the information that was given by the EPA. So you have to find out what is the installation date, was it ever previously lead? All of that information will be here, and you can start to document all of this. And then as you document everything, you can see on the dashboard to your left, you can see all of those main service lines that require replacement. So you can see all of the lead service lines on the map. Now, this is fake data, VCWD, so don't worry. This is fake data. So this is from VCWD. They're currently implementing this. And so basically we're giving you tools just to inventory the system. And so the idea is that you can print this, a report like this out and then send it to the state, then it'll be done. So whatever requirements you have from the government, you can just give us that tool and we'll build it for you. We also work with the backflow and cross-connection monitoring. So you have to investigate and inspect all of the backflows in your system. Same situation, just play the video. Yeah, here. We will select backflow from the map. It will highlight all of the backflows here, and you could select all of the backflows. Here, sorry. Oh, just pause. Sorry. Play video. And then so the fields here, based on the type of backflow, it will show certain tools. Yes. And then just pause. Okay. So based on the type of backflow, it'll fill out certain fields. And so this form is very customizable for backflow test reports. Yeah, you can play. You can see the hazard level is high, and then here you could test for the valve conditions, whether it's closed, tight. You could pause, okay. And then over there, the first step is the initial test. So if the backflow passes the initial test, then there's nothing for the city to do. But if it's a fail, then you can send reports to the client to fix their backflows. You can play. Yes. So here you could see all of the ones that have failed. Those initial failures, we'll send out notifications to the citizens so that they can get a new inspection. So here's the workflow. We have the fail, and then we also have first mail, second mail, third mail. So you can even track when you sent a mail to the customer to fix their backflows. And then finally, we'll send them a pass, and then they will go out and do their final test. And then once it's a final test, then that system is out of so you no longer need to process those failed backflows. So we have built a workflow with Perry from City of Banning over there, so he can help also. Here's the sample reports we built for us, City of Banning. Here's the backflow of non-compliance. And then here's like a test report. It matches the current backflow test reports. We also do a fats, oils, and grease program. So here, the city would like to, investigate all food service establishments and check how they dispose of their sewer backups. So as well, the similar workflow to backflow, we select the tool from the top. It highlights all the restaurants on the map here. We click on the restaurant and we create one inspection. We also have the ability to sign, so the citizen can sign their inspection and the inspector can sign it, and then it will be sent to the restaurant through email. Also, if you need to flag it for follow-up, we can see all of the inspections here that are flagged for follow-up, and these are the reports that can be emailed directly to the citizen. So I think in El Toro, they do the fog inspections, they print it out, and they give it immediately to the client. Yeah. Or we email directly, so it's right there. We also have a GPS, play. If there are no restaurants here, we can add the restaurants also to the inspection. So we have the capability of adding a GPS of fog restaurants and everything, and that could be added to the inspections. Not only fog, we can GPS all assets, valves, manholes, everything, and then that can be part of the inspection modules. And then here is now part of the fog module. Oh, that's it. Okay. Yeah. And so we have a lot of other tools. We have tools for production. We have a fleet management module. Of course, the work order module. We also have modules for sewer line. And of course, we are working with integrations with hydraulic modeling, AI, smart cover, and SCADA systems. So we're constantly expanding. We want to make a great product for you guys. Thank you.
So Aretha, we have a couple questions on Zoom. I think the first question is for Tamai. Will this application accept an extended period simulation model?
Yes, the application can expand into already simulated models. And you can actually, that would be a great thing because we have worked with models which are not really simulated and not even calibrated. So if you already have it, that's a 2-step forward before even starting this integration. Thank you.
And the next question is, can you generate a fire flow report?
Currently, for the current integration, we do not generate a fire flow report, but we have a reporting tool using which you can easily log all that fire flow report information into the system, and we can create reports in PDF, CSV format, or whichever it's needed.
Any other questions?
Oh, yes, Christine.
Regarding the customer engagement module, I know it auto replies to a citizen when closed. Now, can that same philosophy be applied to the work order system? We have certain internal customers who want to be notified when their work order is closed.
Oh, yes, yes.
And
Yeah.
then what about duplication?
Duplication. Basically, the customer sees that there are, problems in that map, so like they can zoom to that area and they can see, oh, somebody already reported that issue.
Okay, so they could see other
Yes.
reports of graffiti, for
Yeah.
instance.
Yeah.
Okay,
Like
thank you.
broken tree, broken street light, yeah. So they could see and do all that.
Okay, thank you.
Thank you.
Any other questions? No? Great. Thank you, Aretha, Tamai. Okay. Our next presenter is XIO Water Systems. So XIO's operation management platform delivers visibility, intelligent optimization, and security for municipal and agricultural water sectors. XIO combines powerful cloud computing and leading-edge IoT technologies together with a suite of software solutions to monitor and control water and wastewater systems. Please welcome the CTO of XIO Water Systems, Marit Bota.
Just getting all the technology working here is always a challenge. And now obviously this screen is the wrong screen for me. Maybe can we just do the PowerPoint one that you have on there? Okay, XIO, what we're standing for is to help people doing this digital transformation much easier, to take away all the pain that they typically have in digital transformation. We have a big analytical platform, and we specialize on real-time information. So currently we get about 90 million data points a day that we store in our historian, and that comes from about 700 different site installations that we have in California and a couple of other places in the world. Our solution specializes on critical infrastructure, and that's important because the business that we're in is critical infrastructure. It's unlike, say, the banks that if they lose your information, or like T-Mobile most recently, it's inconvenient and it's annoying and you're mad at them. In our case, if you mess something up, people land in hospital or worse. There are big issues and we cannot deal with that. So the big issue for us too is to try and make downtime as little as possible, and I will speak to that at length a little bit later. So our customers range from very, very sophisticated partners like what we have here, and I have to say we're very proud to be part of best-in-class solutions like SmartCover, Nobel Systems, and the speakers that you will hear from just after me. So what do? We simplify digital transformation, and we do that by focusing on what is really important. The first thing we do is we eliminate IT headaches. So if you use our systems, you don't have to worry about viruses and updates of everything. We do that for you. We religiously patch all our software. We repurpose our servers at least once every 90 days so that if there is some virus or something embedded there that we don't know about, we can get rid of that. Because what we haven't seen in all of these reports that you hear nowadays about ransomware, like they have at the city of Oakland right now, is you never hear that somebody says, oh, this morning at around about 11 o'clock, somebody broke into our network and by noon, they've got everything extracted. What you often see is somebody says, we realized after the fact, somebody was in our network for the last 7 months. So, and that often happens because people don't know about the inherent insecurities that is in their software. So by having a very solid regime of reinstalling everything in our software on a regular basis, we get rid of that. The second thing is we handle security. We've got experts and we've got systems looking at the security all the time. So I know that we get about, say, 45 break-in attempts, serious break-in attempts to our servers every day. Because we monitor that, we're very aware of what these people are trying to do. And then finally, we provide actionable insights. And this is where data is your friend, right? Because a lot of people use data just for the here and now. So think about a typical SCADA system. How do people use it? Is to say, what's my tank level? Is my pump running? Or if they get really sophisticated, they say, let me get the last 30 days because I need some regulatory report. And after that, the data is gone. And that's sad because data can be your view into the future. It can help you to identify a lot of issues that you may not even be aware of in your systems. So the question would be, why do people want to do digital transformation? The first one is they want to fulfill their primary mission, right? So you see all the great folks here that are about to retire in the water industry. They call it the gray tsunami. A lot of people retire, and very few people are coming back into the field to fulfill their places. So digital transformation helps people do more with less, and that's also a story that we often hear in the water industry. So all the tools that you see around here today is about making it easier for people to do more with less resources. The second thing is improving your bottom line. We've seen Smart Cover's presentation, a lot of emphasis on the amount of money that's saved. And wasn't it interesting to realize that you save money by not washing your pumps because you don't have to stop the traffic? So sometimes there are unintended consequences that things that we have to do can help us with if we have a good digital transformation platform. And then finally, there's the environmental impact. So how much carbon do we produce and what will the impact be on our children if we don't go through a digital transformation? And that's an important thing. We see that more and more. If you've read East Bay Mud in Oakland, if you read their stated goal, it is to be carbon neutral by 2030. Initially, their first statement was 2040. They pulled it back in to 2030. So there's a change with the younger generation coming into the roles that we traditionally fulfilled to make sure that we're also responsible in what we leave behind on this planet. There's another reason why we want to do digital transformation, and that is disasters. They happen. And in the last 5 or 6 years, my definition of what a disaster is changed dramatically. We live in California, right? We thought maybe there's an earthquake and have something go down, and the last big one that I know of was Loma Prieta, and that was almost 20 years ago. So yeah, few and far between, don't really have to worry about that. And then things like Texas happened 2 years ago, where the whole state iced down and they lost electricity for days. But there are other disasters too, right? There's your computer failed. The SCADA system failed and you have a problem with it. What do you do about that? Or you have a PLC running your water system, that PLC failed. So if you think about disasters in a much, much broader context than just something big happening, then we can talk, because when you have a disaster, somewhere in the past, there is something that's your most recent recovery point. And then somewhere in the future, there is some recovery time. In between those times, you have to do stuff manually. So for this initial part is you've got data loss. And what that means is if you have some regulatory requirements that you have to fulfill, somebody has to go around with a clipboard and write things down because you don't have access to your data. On the other side, it is to say you've got downtime. So you have to have people driving around to places to run pumps in hand and check levels because you have lost all your visibility into the system. The questions that you have to ask yourself then is, the first one is, how much data can you afford to lose? The other side of the equation is, how quickly must you recover? Or, if you cannot recover quickly, excuse me, how much will it cost you to provide your service? We have this one customer in Honolulu, and they had an issue where the tank, the reservoir on top of one of the mountains, the instrumentation failed. They're 5 years into a 15-year replacement cycle of their PLCs. So what they had to do is send somebody up once a day to go and take a tank level measurement. 3 hours round trip. So do that for months and calculate the cost. It becomes very, very expensive. So in this context of digital transformation, if you do it right, you reduce that time tremendously. So here's the context. In the 12 years that we've been doing this, our accumulated loss of access to our customers was 90 minutes, 90 minutes. 12 years, 90 minutes. This morning, I received an email from our automated system that our primary database failed. I didn't even notice, and if I didn't get the email, I wouldn't have known, because the switch over from the primary to the secondary system took less than a minute, and none of our customers noticed. So this is the important thing that digital transformation gives you, if done right, gives you the ability to have redundancy and continue doing your primary mission the way that you're supposed to do that. So what's the general architecture looks like? This is it. On the left-hand side, you have your on-premise control system. So you've got your assets, and in our case, what we mean with assets is you may have a pump, you have a tank, booster pumps, lift stations, and all of that. Then in blue, you've got the sensors, the controllers, and the actuators. The sensors, you measure the level or the pressure or the water flow. The actuator switches the pump on and off or change the VFD, and the controller controls that. You may also have an HMI and or a SCADA system that will interact with those systems. And what I don't have on there, that's the new kid on the block, is IoT. And I heard this, that's the beginning of a rap song, is IoT is in SCADA, or is hot, SCADA is not. So if I were to be a rap artist, that would be the song. So IoT is hot, SCADA is not, and the reason for that is you get a much better view for very, very cheap. And I'll show you a couple of examples of that. So we have this on-premise system, and then we have this gateway device. Nobel referred to that just before this session on how you can extract data in a secure way from an existing SCADA system and put that on the cloud. Then on the cloud, we've got a historian with analytics and digital twins and fancy alarms and fancy reports and all of that. But you have secure user access from any device with a web browser. And on the other side, you've got external APIs. And why that's important is the 3-4 companies that you see represented here is in the same customer base, but we fulfill different missions. So we're non-competing, but we give you a much better view of your system than either one of us can do by ourselves. And the ability to display information from our partners on our portal, or they from our portal on their views, makes it so much easier for you to train your personnel, because now they don't have to learn multiple systems. So this is what we're going to talk about, this general architecture. The other thing that's great for digital transformation is NGOs. We've got many NGOs in the US doing fantastic uplifting work to provide water for places in developing countries. It's a very sensitive issue, though, because it is very expensive to be poor in a developing country, because you don't have water running to your house. There are no pipes. So you've got these water vendors with carts selling bottled water to people to wash with and to cook with and to drink. Imagine how expensive that is. So when an NGO comes in and say, hey, we will give you clean water, you have issues because you take away the livelihood of these water vendors. So by having a system where our NGO partners can install something in Nairobi, Kenya, and have the ability to monitor it from California to measure the water safety, and also to help train people to be the next generation of water operators, is an absolute game changer. Digital twins. You must have heard this concept many, many times, so here's my take on it. It's not the real thing. It's some approximation of the real thing. So maybe this is a digital twin of me, and if you use a little bit of imagination, you can see, yeah, it's probably, could be me, but it's not a very good representation. But at least if I start there and have, say, a few sensors that will give me this information, I can add more sensors, and this is where the IoT devices come in. So with more sensors, I can have a much better idea of what my physical system is. Or if I go further and I buy a fancy digital camera, I can get a much bigger picture. The point still is, this is not the real thing, but it gives me a very good idea of what the real thing is like and how it will change if something happens to it. So this is how we use digital twins. We use it in scheduling. So one of our customers had a very traditional system. They have float switches in a tank. Float switch goes down, pump starts. Float switch goes up, pump stops. And they spent, on average, couple of years average, they spend about $35K a month on electrical energy. They pumped 75% of their water off-peak times. It's just purely random. So they, the rest, they pay peak prices. That's about 5-6 times as expensive as non-peak prices. Then they said, oh, we'll use timers in our system. So they put timers on the devices, and they were able to increase the off-peak pumping times to 83%, reducing their electrical energy bill on average to $31,000 a month. When we came in, we implemented smart control. And what the smart control does is it says, we've got a digital twin model of your tank. We understand seasonality because summer is different than winter. People irrigate. People go away on Thanksgiving weekend. All of that built into the model, and then change the algorithms so that we only pump in off-peak times. So we make sure that we start the pumps so that the tanks are full at the times when the rate change occur. So in the audit period there, we pushed up their smart control using non-peak times to 93%, bringing their energy bill down to 27%. And if I may add, that 7% included a massive leak that they have. I'll show you an example of that leak a little bit later. If it wasn't for that, we would have had 1 or 2% pumping in peak times. So a major benefit for this utility, because month after month, year after year, they save on average $6,000–7,000 a month. And that's not something to discard easily. Here's how we do it. So you typically see this pattern, right? Is tank fills, drains, fills, and then you see this little tooth there just below where it says steel tank. That's a top-up cycle. So the tanks were full, and then based on the digital twin algorithms, we determined that we will not be able to run through the session before the rate change occurs. So let's top up the tanks so that by the time the rate change occurs, we still haven't started pumping again. There's another view on scheduling, and that is carbon cost. So I shared the example of East Bay Mud. This is a very common pattern. You see this with electricity use, you see that with water. Makes sense, right? Middle of the night, people use very little water. Then around about 4, 5 a.m., people start waking up. Then around about 8 o'clock, everybody goes to school, use a lot of water, take a shower and everything. So then you've got a gradual decline for the rest of the morning. Evening, people come back, they go to the gym, they come back and have a shower, and this is their water consumption. So one of the utilities that we work with use this just generic pump cycle that I said earlier, and their audited results were that they typically pump 700 gallons of water for each pound of carbon dioxide that they use. Now, what's sad about these rate structures of PG&E and Southern Edison is that the peak times are between 4 and 9, or noon and 9, depending on where you are. And if you look at the yellow curve there, that is the contribution of solar cells, right? So at 8 o'clock, you see a huge increase in the amount of power generated by solar. But there's not a lot of benefit, and it goes to the afternoon and to the evening in the summer months. So by shifting the pumping cycle to wherever you have the peak in solar electrical production, a second utility increased the amount of water that they pump to 8,000 gallons per pound of carbon dioxide. So more than 10 times improvement. They didn't pump less water. They pumped the same amount of water, but they used way, way less of carbon dioxide, making the environment for our kids much, much better. The sad thing, though, is that the incentives that the utilities currently have do not help us to use electrical energy when we have a complete abundance of photovoltaic electricity available. So about 3 years ago, the spot price in March, I think of 2019, the spot price of electricity went negative in California because of an oversupply of photovoltaic electricity. What that meant is we paid Nevada to use our electricity. Do you think how sad that is? Because there were so many pumps that we could have just turned on to use that excess electricity. Here's another use of digital twins, and that is for leak detection. We focus, in this case, in this example that we use, we focus on smaller utilities. Typically have a tank, and we monitor the tank level, and then from that calculate the usage. But it's a little bit complicated because, you know, as you pump water at the top, you get sloshing and then you get all kinds of bad measurements. So by using a digital twin and using great analytical functionality, we can detect leaks. So you can see there, the 14th of August, there was a leak, and round about the 28th, they were busy fixing that leak. Took them 2 weeks to find the thing. So think about the old days, how people looked at leaks, right? Is how do you detect a leak when you're a small utility? First, you have to be aware. So if it's not obvious on the ground where you see the water seeping out, you only know that you have a leak when you get your next electricity bill. So suppose it takes 30 days for the bill to get there. You may have had a leak for 6 weeks, and you didn't know, but your pumps were running all the time, and you didn't notice because you didn't have full-time staff at your site. What makes it more tricky is, as you can see here, is a profile for the water usage at that utility for a year. In the summer months, some of these peaks, say around about July the 16th, are the same as the leak that you see towards the winter. So the algorithms have to be smart enough that they can detect a real leak in the summer and not ignore a leak in the winter based on the amount of water that's being used. This is what these folks found. So 8 feet underground in a dry riverbed, that was where the leak was. So again, the digital twin virtual water meter alarmed these folks within 15 minutes of the event occurring. It took them 2 weeks to find. So, but compare those 2 weeks to the old days where you had to wait 30 days before you get your electrical bill and then tag 2 weeks on top of that to figure out that you actually had a leak. Another example is here we use a model of a well and the pumps associated with it to optimize agricultural pumping. What you see there is the profile of the water above the pump, and you'll see towards the end there's a peak. That's when the rain started. The aquifer started filling up again. All these combs going down. That's whenever you pump. So whenever you pump, the water goes down. When you stop pumping, it reverts back to the top. The impact of that is significant because you design a pump for a specific head and a specific flow. If your head changes, like it changes there, around about 10 feet, you're not at the optimum point of your pump anymore. So by using that knowledge, our customer has 11 pumps, and what we do is we measure the energy intensity once a week for each pump, because as the season goes, the energy intensity changes because the head changes. And then, as you can see here, we've got different trigger levels on the pump. That one triggers at 13 feet. The second one example there is the efficiency order. Each one of the pumps are rated based on their efficiency. We can also take a pump out of service, and then finally it shows us which pumps are actually running. So by doing this, we save them a tremendous amount of energy. We work with Linkus Engineering that work with Southern Edison in this incentive. And as you can see from this graph is the blue bars there show you the amount of acre feet pumped in this year that they audited the system based on the pump. So pump number 7, that is the most efficient, and that's the orange line there. So it shows you the kilowatt hour per acre feet. So the one that was most efficient pumped the most water. We had to run the other ones because sometimes the demand is just too high for a single pump. But you can see pump number 9, that's the least efficient of them all, hardly run at all. By using this, the amount of energy that they used dropped dramatically, say almost 5.4 gigawatt hours that they use in a year dropped down to 4.4 gigawatt hours. And the nice thing about that is it saved them $110K per year. Now, this is free money, right? Because they didn't pump less water, They pumped the same amount of water, but using the data that we could get from the system as well as the historical data, we were able to save these guys $110,000 per year in perpetuity. We also implement artificial intelligence algorithms. Somebody earlier mentioned ChatGPT. Funny story is, friends of ours, a daughter-in-law's husband is their son is a doctor, and his wife said to her husband, "Hey, let's try ChatGPT." So she started typing questions, and the thing answered. And in the end, it says, based on all the symptoms you describe, you're pregnant. And that's how she announced the pregnancy to the family. So I thought that was a nice idea of a great use of artificial intelligence. So state of California, Caltrans, they've got all these rest stops next to the freeway. We've got 13 different districts, and right there where I-580 meets I-5, just about an hour and a half on a good day out of San Francisco, there's Wesley Rest Area. We do all the water and wastewater treatment and production. We handle the control of that system for them. And this is how we applied our artificial intelligence algorithms. So it looks a little bit busy, but all the black dots that you see there is the amount of water produced per day. Now this spans 2017 to the end of the year last year, and you can see seasonality that you would expect, right? Because people travel more in summer than they have in winter. And then we've got a light blue and a dark blue graph, and all that says is our confidence that the amount of water being pumped will be in that range. So in itself, not really useful. Why would you use that? But then we use our artificial intelligence algorithms to extract information from that. And you see in the top graph there, there's a decline, and there's a particularly steep decline between a long-term trend between 2018 and 2020. And now we know it's COVID, right? So COVID caused people to travel much, much less. The second one is also interesting because it also makes sense, right? During January, people travel less. February, May, they start traveling more. July 4th, absolutely, everybody's there. And then if you get to November, you see, oh, there's a peak there around about Thanksgiving, Christmas time. Makes a lot of sense. Then you look at the third graph there is to say, so what's the weekly trend? And if we start on the Friday, you see, wow, Fridays, there's a lot of water being pumped. And then you think it makes sense because between San Francisco and Wesley is the Altamont Pass. And the traffic on the Altamont Pass looks like the traffic in Los Angeles. It's a parking lot. So by the time you get to Wesley, everybody wants to run to the bathroom. So it makes sense that on Friday evenings, people want to go to the bathroom and they stop. You have a lot of water production. Saturday, they're all at Yosemite already. So nobody travels. And then coming back on a Sunday, you see increased water production. But now people don't want to stop because they're heading home. And then you can ask, how do I use this information? And then it becomes obvious is now this becomes a tool to say, if you have to do urgent maintenance, don't do it on a Friday. Do it on a Tuesday. Because Tuesdays are the days where people typically use less water. If you have a big thing that you have to do, don't do it in July. Do it mid-January, February, because that's when people use these services the most. But what you can also do is to say, now that we have this knowledge, we can use this a little bit as a crystal ball and look into the future. And now I've got two confidence bands. The lighter one that says, I've got an 80% confidence that the amount of water that we need to produce will fall in that band, or a 20% one that it will fall in the dark band. So all of a sudden, something that was very, I don't know, don't know what it does quite, becomes something that is extremely, extremely useful and help people to plan their year ahead. We also implement analytical functions. If you're involved in wastewater, you know these pictures really, really well. And it's always difficult for people to say, how do I respond to this? Our analytical functions for lift stations will give you this dashboard. At the top, you see the pump cycles, and at the very top there, you see these little black bars, and those are the statistical bars where we expect these pumps to run in or to be efficient in. And if it's outside that range, something may be wrong. But so the pumps can be pucked up, it can be clogged up, it can be blocked. You don't know, and it can recover itself. But we also give people, especially for operators that are busy, on their smartphones, this lift station health graph that says good, bad, or it's not that bad, or don't worry at all. And then on the left-hand side, on the right-hand side there, you can see there's a log that shows all the events that we detected from the system. At the top that I'm not going to show, you'll see there's a 12-month range as well. And what's great about the 12-month range is when you look at the efficiency of the pumps over time, because you've got lead lag with alternation, you expect the pumps to deteriorate at the same rate. And if they don't, you know I have to go and replace that pump. So by seeing the information side by side, it helps you to identify inefficient pumps immediately. We've spent a lot of money and effort in creating our data platform. So we also have third parties using this as a private labeled portal. We've got this one company in Berkeley that uses us to collect rainfall data and display that, because they say they're geologists, their business is geology, they don't want to deal with the cloud stuff, so they use our platform that's customized for their use. We integrate with other providers. You've heard a lot of talk about that. Channel Island, just east of here, northeast of here, use us to monitor all their wet wells and control all the pumps for their lift stations. But they also have a very elaborate installation of smart cover devices. So here is the dashboard that we show the integration with smart cover. You can see the map of Channel Islands there, and I just hovered over the H station device there. You can see what the level is that smart cover measures. And since it is now integrated with our historian, you can also see the longer term trends of the smart cover. Now, what's great about that is, coming back to the digital twins thing, is now we have a lot more visibility in how our system performs. We had a very singular view of the wet well itself. By getting the smart cover information of the amount of effluent coming into the wet well, we can change our prediction algorithms. So by having IoT devices give you a much better view of what's happening with your system, you can improve the overall efficiency of your effort. So the takeaway today is all cloud solutions are definitely not equal. So if you go for a cloud solution, make sure you go for a partner that can handle multiple sources, that is open, that would allow somebody else to connect their information to you, or your information to them, so that you can see it. So bottom line is, don't get painted into a corner. Get a platform that can grow with you. But if you look at the 4 vendors here today, is the bottom line is, we and our partners do the heavy lifting so that you can focus on your jobs. Any questions?
No questions? Okay. Thank you, Maritz. Okay, our last speaker of the day is Fracta AI. Fracta AI is a leader in development of machine learning, a subset of artificial intelligence that gives computers the ability to learn without manually being programmed by a human. Fracta uses automated and specialized algorithms to learn patterns in very large data sets, detect anomalies, and identify new or previously unknown insights. Please welcome Max Heiberg.
Good afternoon, everyone. Dave told me that I could spend as much time as I'd like. However, I did hear that there is a happy hour after this, so we're going to do the smart thing and keep this shorter rather than longer. Though I am an AI company, but I don't know how to work chords, so give me 1 minute here. Is that in there? Yeah. Is it going to pop up here, or? There we go. All right. Hello again, everybody. First off, I want to thank Nobel for putting on this event. This is actually my first time in Southern California, so I was excited to come down and make the trip. I'm from Minneapolis, Minnesota originally, so I heard everyone complaining about the weather, and I didn't really understand because I left and I had a foot and a half of snow coming. So I'm actually pretty fortunate because I missed out on shoveling. But thank you again, Nobel. I really appreciate it coming down, and I appreciate it. Now, my company is Fracta, and we've already had a little introduction into Fracta thanks to Tom at Roland, who is currently actually using our software, our services, I should say. But my goal today is to introduce you to Fracta, introduce you to our technology and how we work with Nobel Systems, and then also introduce you to kind of how we've been implementing our systems throughout our client base. A little bit about Fracta first. We were founded in 2015. We're out of Palo Alto, California. We like to call ourselves an old machine learning AI company and a young water company. We were recently invested in, shortly after our founding, in a company by Kurita Industries, which is a large global water treatment company based out of Tokyo. And this has really allowed us to expand our horizons beyond just the United States and North America. We partner with over 100 utilities worldwide. So this includes North America, Europe, so Germany, Spain, Italy, and France, as well as Japan. Japan is actually one of our larger client bases, as our founder is Japanese himself and our parent company is Japanese. So we've been getting a lot of investment and R&D actually coming from our Japanese clients, which is great because then we can come and bring them to our clients here in the US. Well, what are we actually doing, right, with machine learning? Because it's a very big, broad term, and it's being thrown around a lot right now in the industry. So I want to make sure that we're very aware of what Fracta actually uses machine learning for and what we don't, right? Fracta is not a real-time data assessment collection. We're not using real-time data. This is a desktop condition assessment study. So I went on to the AWWA's website. I kind of pulled out what they recommend for basic desktop condition assessments because this is where we fit in, right? And the whole idea behind a desktop condition assessment is using data that you already have in your system, right? It's not about collecting new data. It's about making decisions with the data that you have available. Mostly this is to figure out certain things for your pipe network, right? Likelihood of failure, consequence of failure, remaining useful life. Those are kind of the big three in which utilities will use to plan moving forward. Fracta's idea is how do we make that more efficient? How do we make it better? And how do we take advantage of all the pipes out there, right? And not just the single utilities. So I used to always include this slide in my presentation, but now that ChatGPT has come around and I'm in California, it seems that a lot more people understand machine learning, right? Being from the Midwest, sometimes half my job is explaining what AI is. But for the simple version, right, machine learning is basically just a version of artificial intelligence, and it's algorithms, and it uses and analyzes data using machine learning. For machine learning, data is very important. And the reason machine learning works for desktop condition assessments is the databases surrounding water pipes and water main breaks fit perfectly with machine learning. There's a reason that we're focused on the water industry and not the sewer industry right now. It's because the models and the data sets that are available fit perfectly and they work well with predicting water mains. It's a lot different when you get to sewer systems, so that's why we're not going to touch on that today, and that's why Fracta's focus and technology currently available is strictly for water distribution networks. I'm listing some data parameters, right, on what's necessary to actually use Fracta and use machine learning, and I'll touch on this a bit, but I want to make it very, very clear that not a large amount of data is needed. Roland brought up hydraulic models, some very specific data parameters that we're happy to take, but at the end of the day, machine learning is a simple tool to use and it doesn't take very many parameters. Coming from a utility themselves, all we're really needing is your GIS system and your break history. And we'll get into that in a bit. But the important thing to understand here is that data is key. Collect your data. I don't know how many of you are collecting your water main breaks and water leaks and storing them in an Excel file or something like that. But I recommend that. Even if you're not using machine learning in the future, right? Track your data, track your breaks. That information is valuable. As everyone around here has been talking about, you know, it's all about using data to make predictions. So even if it's old data and you don't think it's good, it's valuable, and hang on to that data piece. All right. Differences of our machine learning technology versus a lot out there, right? We're not using any hardware. We're only taking your data sets in shapefile format. It's fast because there's no integration with tools, there's no integration with and waiting for data to come. It can be returned pretty quickly in a 4 to 8 week time period, basically giving the algorithm time to run. And this is the last one I'll touch on, is the constant improvement. Many utilities are doing condition assessment with LOF and COF maybe every 5 years, every decade, right? And they're doing a model and then they'll let it sit on the shelf. The difference with machine learning is it's constantly improving, right? That's the one of the major benefits of AI is that you're not just relying upon a single model, a static model in time, but you're actually looking over time and improving it as situations arise. Just a quick glance. I know you've seen this earlier at Roland's, but this is a cutout of what our software service looks like. While we have integrations with Nobel, obviously, and our API, I wanted to show this and give you a little insight into what we're actually providing clients, right? So we're looking at likelihood of failure right now. Now, we also provide consequence of failure, total risk, and remaining useful life. But likelihood of failure is kind of the main driver and the main algorithm that utilities like to see on their pipe network. So we provide 5 years out of LOF scores that include a percentage for failure as well as a risk rank. We provide a remaining useful life for that pipe. We provide the risk drivers associated with that pipe. So what is the algorithm actually thinking is causing the harm on that pipe, right? What's causing that risk? Instead of having a black box, we want to actually provide insight in what to the model and the algorithm thinks is driving risk at that pipe segment. So just a quick cutout of what our software looks like, but also our results. The rest of this presentation is going to be technically focused on exactly how the machine learning model works, and I hope that's all right. You were able to get a nice overview of the system from Roland, so I hope this is kind of you can think of your own network and your own system and see, you know, are you ready for something like this, and where are you going to be in the next few years, right? Question in here, does anybody do, like on a yearly basis, a likelihood of failure scoring for their system? Or does anybody have those types of analysis done for their network? Okay, you do. How did you do it, if you don't mind me asking? You utilize software, great. That's what I like to hear. A lot of people say, oh, well, once a year, right, we look at the material type, the age of the system, and then the break history. That's a start, right? That's an analysis procedure that works great for many utilities. What machine learning does is take that to the next level, right? A local model will have the asset information and history. It'll have maybe a few geographic parameters, maybe. And then they're using just their data sets, right? Machine learning goes above and beyond that. We try to take that to the next level, and what I'll get into here is how exactly we separate ourselves from a standard modeling procedure and how machine learning actually works with your data. Here are the big four. So there are 4 differences between a machine learning likelihood of failure analysis and a standard likelihood of failure analysis, right? The first one being data parameters. So this is what are you looking at when it comes to understanding the risk of that pipe. Obviously, age and break, right? We want to know the material type, we want to know the history. The second being network effect. So many utilities are currently, in fact all of them, are using just their own data sets, right, for understanding the risks associated with their pipe. And they're also not improving it very often. How often do you improve, or do you update your model? It sounds like you're using a software, so maybe a little bit more often.
Yeah, I mean, we took into account like hospitals.
Yep, we'll get into that, exactly. So there's a large data sets, right? And you can spend a lot of time pinpointing them. And that's exactly right, that's where we're getting at, is there's much more out there than just the standard variables that are in existence. So we'll talk on kind of that in a bit. But when it comes to model improvements, machine learning modeling will improve continuously. Every time a new data set's available, it updates itself and provides a new model. So when someone's using an AI-based likelihood of failure, all they would need to do, right, is provide a new break history data set, and they would get an updated model. So that's kind of the benefit of this, is instead of having to redo the whole process in another year, you just add in new information, and it spits it out very efficiently. The last one, I'm going to touch on this one first, actually, is weight-based. So if you look at the AWWA manual for desktop condition assessments, they stress heavily how weighting certain criteria points, right? Certain issues, certain data points are going to have higher weights of stress, right? An older pipe is going to be weighted more than a younger pipe. Machine learning disregards all that. Nobody's telling the algorithm what you should rank a pipe at. The whole idea is cause and correlation. What is the history of that system? What is the history of that pipe network? And what's it going to look like in the future? We're not telling it anything, it's learning for itself. And that's that's one of the big ones for machine learning, right? Is there's no human interaction to make assumptions about a network or something like that. So let's talk about data parameters first. So the only thing required by the utility to make this work is age, material type, diameter, obviously the location of the pipe, but then your break history. So if you don't have it or you do have it, those are the key parameters that you're going to need. The rest of what you see here has already been curated by Fracta. We've built an in-house database of around 160 different parameters that, again, outside the pipe, right? So we're not looking at pressure, we're not looking at flow, we're not looking at the type of water. We're looking at outside parameters. Obviously, as we move down the line, there's a lot of sensors, there's a lot of technology out there that will take that to the next level. But for this time, we're solely focused on the pipe's conditions and surrounding the outside conditions. So population, right? Land use, hospitals, is it a road? Is it, maybe it's a farm field, right? Where is that pipe located? I know we have some under Children's Hospital. That's a lot more valuable, right? A lot more dangerous than a pipe running under Farmer Joe's field, right? So that's very important when it comes into it. Also climate, terrain. Around here, elevation. That's a big one we hear all the time. If we have the elevation, that's how we know where your pipes are at, right? And that's very important in understanding the risks associated with them. Here's a good look at kind of visualization of that data, right? So this is Arlington, Texas. But you can see these are just 2 examples of some of the data that we use. But you can see how when you look at a system, how it actually plays out. So for soil pH, right? I don't know if everyone has their system mapped, but this is what it looks like if you were to just pull it up and say, what's my system look like in comparison to the pH, you know? Or distance from major roads. Where are my major roads and where are my pipes located from them? Instead of having a GIS tech spend all day, let machine learning AI do it, right? I mean, I'm not doing it. You can guarantee I'm not going to spend all day trying to figure out where your pipes are. We have an algorithm for that. That's where machine learning comes in. And of course, we have these for 160 different parameters. These are just too easy to show examples. Constant improvement. Now we're getting into kind of the global aspect of AI, right? But the whole idea with machine learning and AI is you make a prediction, and then you test and eliminate that prediction, and then you make another prediction. So when it comes to water mains and predicting a likelihood of failure, it's kind of a four-step process. We make our initial prediction, so this is that first AI model you receive. You then test and eliminate that. Well, we would love it if you went and dug up your entire network and told us the condition of every pipe, right? Not gonna happen. But I bet you're gonna have a water main break, or you're gonna have to replace some pipe, right? There's things that happen throughout the year that you are documenting and collecting. When you have a new data set, maybe it's 6 months, maybe it's a year, maybe you had 20 breaks in a month. I'm from Minnesota, so February, all our pipes break at the same time, right? But when there's a large data set available for you, you plug it back in, meaning you send it to us, right? Or to Nobel, whoever your provider is. That's the extent of it. We collect that data, and then we retrain the algorithm. And this is where the value comes in, as you'll see, is this isn't just a 1-year deal. This isn't just a 2-year deal. The more data and the more time you have, the better the accuracy gets. Second part of that, too, is it's not just your data. So if you saw on the slide earlier, we have around 180,000 miles of pipe that we've analyzed. Now, that's not our pipe, right? That's everyone else's pipe. That's all our clients. That's everybody who's ever sent us a data set. But it's all in our global algorithm. What makes this so great is that depending on the size of the utility, the amount of data they have, you're able to get a customized machine learning model for your network. So if you look at the top, just picture every pipe in the US, right? Pretending that we had every single client, would be in that global algorithm. When you want to come on board and you want to run a machine learning model for your system, it's going to get personalized. It's not going to be a standard machine learning model, right? So you can kind of see how it's broken out into 3 different clients or customers. You have, and it's all dependent on break history and data. So you have someone with maybe 15 years of break history, someone with 10, someone with 5. Break history is the best determining factor for likelihood of failure in a machine learning model because it's the event we're trying to predict. So what that means is that a utility with 15 years of data, 10 years of data, right, you're going to be able to get a personalized machine learning model just because your data history is fantastic. If you're a smaller utility or a utility that hasn't experienced much break, that's all right. That's actually better, right? You're having less water main breaks. Good for you. You may not get the best personalized machine learning model, but who cares? You're not having water main breaks. But the idea here is that we can tap into that global algorithm and basically pull out pipes that are exactly similar to yours or close enough, right? And start using those for comparison. So we can say, all right, you may not have very many water main breaks, but guess who does? San Diego, right? Let's use their data set, some of their data sets. You don't get to see it, right? It's behind the wall, so you don't own their data, but we get to take advantage of their data by learning from their history and learning from their pipes. And that's one of the major benefits of AI is that if you are a smaller utility and you don't have the size of data sets or the amount of people to work on it, you can still take advantage of it for a very cheap price comparatively because you're just a very small data set. So this is how the global algorithm really interacts with our various users and our various clients, depending on their size and their cleanliness of data. Accuracy, the last one, right? Everyone wants to know, well, great, your modeling is fantastic, it's a great sell, is it accurate? How are we going to use it? And this is where we come back to that continuous improvement and that improvement over time. We compare it on the first year to an age break model, right? That's a pretty standard model to compare it to, but when you look at it and you look at the top 30% of your pipes, so the top risk tier, right? Those pipes that are on your highest level of concern, what is the accuracy of breaks in those? Are we hitting our mark? The answer is yes. It's not 100%, so we're not a magic ball, right? No one's here to say that this is perfect. The idea is to get as close to perfect as we can. That first year, we're predicting about 54% of the main breaks within a system. And that climbs year after year. And this is what I talked about when it's a continuous improvement, is that every time you upload a new data set with new history, the model's going to get better because it's going to learn from that. You may have a lot of breaks that we didn't predict that first year, but we tell it, and it's going to go around and say, all right, I understood that. Let's apply new rules and new conditions to that. So our accuracy will grow and grow year after year based on more data being provided. And even if you don't have any new data, somebody else is going to have new data, and somebody else is going to be bringing it in. And what we're really looking for is to get closer and closer to that 100% hit rate. We're not there yet, but we are still a young company. So if you give me all your data, maybe we can get there someday. But that's how we are tracking our accuracy over time and showing it that it's not just a one-time event, and that using your data year after year will eventually provide better results and better accuracy moving forward. Case study, right? Last one, and then we're done. I think I'm pretty early, but you guys seem like you're ready for a break. So how do you use this? How do you use our results? I'm sure every utility is different, right? Maybe it's capital planning. Maybe you're trying to convince your commissioners that you need 5 million, I don't know, how many more millions you need to fix pipes, right? How do you convince them that? That's one of our biggest users, as well as throwing alongside pavement repairs. I don't know how many of you have to deal with the road crew in your city when you're making plans, but in the Midwest, that's huge, is the roads come first, water comes second. So what we see a lot of times is people combining it with their standard replacement plan and using our results to move from there. But the one I wanted to touch on, which I think is more important down here, is non-revenue water loss and leak detection. We are not a leak detection company. Our service is not called leak detection. We're not out there detecting leaks, but what we found is that high likelihood of failure pipes usually mean that pipe's leaking already, especially in places where you're not using PVC. Now, down here, that obviously may be different, but the idea is that a high likelihood of failure pipe is going to correlate to most likely a high leaking pipe. So one of our utilities users in Pennsylvania used us specifically as a leak detection tool. We just want to find leaks in our pipes. So they took our top tier risk pipes, sent out their crews, did standard acoustic leak detection, whatever their method was, and it ended up finding leaks and reducing their NRW 20%. Now that's absurd, especially around here if you have that much non-revenue water loss, but in Pennsylvania that's obviously more common. But the idea was that this could be implemented in your utility's own needs. If it's convincing for more money, if it's planning for the future, maybe it's a tomorrow problem, right? I have a leak detection crew that spends too much time finding not enough leaks. Maybe you have one of those fancy dogs, right, and you wanna have it go out and do something. How do you prioritize your crews? How do you prioritize your time? And that's what this is coming down to, is taking ideas, taking your data, and then providing it in useful information. I told you to be short and sweet. I kind of got a nice sell from Roland this morning, so I'm going to leave it at that. But are there any questions for me? Yes, sir.
Introduce you?
You don't want to say closing message or? You don't want to say.
So my question is, you mentioned the first year you're predicting 54%. So if we can go back to that slide, does that increase if you have 15 years of data versus 5 years of data? Or how does that?
Yeah, the more data you have, the more accurate it's going to be. I heard it earlier, garbage in, garbage out. But if you have the larger the data set you're going to be, the more accurate we're going to be. I don't have like a number on what the accuracy would be there, but the only thing we hear from our data engineers is give us more data. So if you come in with I had one client, I wish he signed up, but he had every break back to 1974. And I'm like, give it here, right? We want that. That's the kind of data set that's like our dream. So it will increase. I can't guarantee it, what the percentage is going to be, but all we know is that the more break history you have, the more accurate it's going to be, which is unfortunate because that means you have a lot of breaks. But obviously that's kind of where we're going. Does that answer it? Perfect. How are you being the soil type? So we pulled from national databases. I don't have the exact ones, but a lot of universities we purchased them from. The National Geographic Society we purchased them from. They're all publicly available domains that we pulled from. We just curated them. That being said, again, on the data portion is, we'll take whatever you have. If you have soil test sites that you've done, give us the data, right? If you have a hydraulic model, please give it to us, because that'll actually implement in our consequence of failure tool, which I haven't even touched on, right? So if you have data sets that first off, are good, they're valuable, and we will take them, or we'll at least have a conversation around them. But we've pulled all our databases from publicly available domains, and we've paid for them, obviously, but then they've been curated over time.
How does pricing vary by size of?
Utility. So usually it goes by, and again, you want it, we work with Nobel, so you can actually talk to them on the agreement size, but usually it's based on size of the data set or equivalent miles of pipe or service connections. So, you know, a small utility could be $5-6 grand, and then you get some of the bigger ones, and we'll cap out at a certain level of price. But it's a size of the data set or size of the system. All right. Do I get to break everyone?
Hope you all enjoyed the conference so far. So sorry guys, I'm still under the weather, but my doctor asked me not to talk too much. So let me finish it up faster. Plus the happy hour is also waiting for us. Dear speakers, audience members, exhibitors, and all workshop participants, we would like to extend our heartfelt gratitude for your participation in this workshop. Your active engagement, insightful contributions, and passion for the topic have made this event a resounding success. To our live speakers, Tom, I think he's not here, Mike, and Ms. Sorako Paluga, and video speakers, Chris, I think we have Christine here from Fountain Valley, and Danny from Mission Springs, Randy, and Randy. Thank you for sharing your knowledge, expertise, and perspective with the audience. Your presentations were thoughtful, provoking, and inspiring, and we hope they will continue to spark meaningful conversation and actions in the future. To our audience members here, as well as the people who attended in the Zoom meetings, thank you for your attentive listening, insightful questions, and eagerness to learn. Your active participation has greatly enhanced the quality of the workshop, and we are grateful for the opportunity to connect with you. To our exhibitors, XIO, Smart Cover, and Fracta, thank you for showing your products and services and for your support of the workshop. Your presence has added to the overall richness of the event, and we hope you have found it valuable. Finally, we would like to thank everyone who played a role in organizing and supporting this workshop. Your hard work and dedication have made it possible for us to bring this event to life and create a meaningful experience to all. Once again, thank you all for your participation, and we look forward to the opportunity to connect with you again in the future. And at the last, we should not forget to thank the technology. Thank you, ChatGPT, for giving this nice write-up. Just ask the question, 5 seconds, you get the answer, okay? Thank you.
Finally, before we go, we have a few raffle tickets. So, who's going to pick them? You? No, you do. Yeah. 3741038. I don't think anybody. 3741038. Oh, Brian. So you get, doesn't matter. So Brian, here you go, you get a $100 Visa gift card. Thank you. That was good. 3740991. Yes, that's you. So this is from Nobel, a $100 Amazon gift card. Thank you very much. 3740931. 931. Wow. Thank you. Just to let you know, the City of Lemoore is our newest customer. It's a good welcome to Nobel family. Thank you. No. So that concludes our session. Thank you all for coming. And as Balaji said, he's already given his thanks. So we can break now for a happy hour. And there's some alcohol and drinks and snacks outside. And please help yourself. Thanks.